Hello, and thanks for using TickBoom. In this question, we're told that the triangle OAB to the right has M as the midpoint of AB, and we're told to let vector OA be A vector, vector OB be B vector, vector OM be M vector, and vector AB be P vector. So it's kind of just the definitions that we're told to deal with. Part A of the question says write vector P and vector M in terms of vector A and vector B. And then part B says to hence prove that the magnitude of vector P squared plus 4 times the magnitude of vector M squared is 2 times the magnitude of vector A squared plus 2 times the magnitude of vector B squared. Now the student who sent this through was really only struggling with part B, but because the two parts are quite linked, what I'll do is I'll work through both of them just for completeness. So for part A, what I might do to start, I'll just recreate this triangle. So we're given this triangle OAB. We're told the point M is the midpoint of AB. Then we're given our vector notation. So from O to A, we call vector A. From O to B, we call vector B. From O to M, we call vector M. And from A to B, we call that vector P. Alright, and our challenge is to find vector P and vector M in terms of A and B. So if I start, say, with vector P, so vector P is basically the vector AB. So in going from A to B, we can get there by going from A to O, and then going from O to B. Going from A to O is the same magnitude as this vector A, just the opposite direction. So that's minus vector A, and then OB is just vector B. And AB we're told is vector P. So therefore we can kind of write vector P as being vector B minus vector A. So that's the first bit. Vector M, so we can think of the vector OM. The way we could get there is to go from O to B, and then to come from B to M. O to B is just vector B, that's what we're told. B to M is half of the magnitude P, because we're just going to the midpoint, and the opposite direction. So it's minus vector P on 2. So that's going to be vector B minus vector P, which we've just worked out as vector B minus vector A, all divided by 2. So that's going to be vector B minus vector B on 2 plus vector A on 2. So vector B minus vector B on 2 would just leave us with a vector B on 2 plus a vector A on 2. And so I'll just write that as a half times vector A plus vector B. So I think that's part A of the question done. We've got our vector P and our OM is vector M. So we've got our vector P and vector M both written in terms of vector A and B. So now what I'll do is I might turn over to think about part B, which was asking us to prove that the magnitude of the vector P squared plus 4 times the magnitude of the vector M squared is equal to 2 times the magnitude of vector A squared plus 2 times the magnitude of vector B squared. And I think the way to tackle this is to just first look at magnitude of P squared and magnitude of M squared, and then bring them together and see if it simplifies. So if I start with the magnitude of vector p squared, that's going to be the magnitude of what we just worked out in part A. So that's vector b minus vector a squared. And here's where we can use a result that, if you're not familiar with this result, it's definitely one to be familiar with. And what I might do is, just in case it's not something you've come across, I'll separately prove it. And then I'd recommend you kind of either commit the proof to memory or the result to memory, or both. But for vector b minus a squared, we can write that as vector a squared plus vector b squared minus 2 times the dot product, so a vector dot b. So let's leave that there. I think that'll come in handy. Vector m squared we can write as the vector and what we just showed in part A, so a half vector a plus vector b, so that magnitude squared. So the half squared I'll just bring out because that can be written separately as a quarter, times the magnitude of vector a plus vector b squared. And I might just bring up this 4 because that's the format we've got in our questions. So 4 times the magnitude of vector m squared is equal to the magnitude of vector a squared plus the magnitude of vector b squared. And once again, there's a result here that if you don't know it, I'll also prove this one. But this can be written as the magnitude of vector a squared plus the magnitude of vector b squared plus 2 times the dot product of a and b. So now bringing this together, we can conclude that the magnitude of p squared plus 4 times the magnitude of m squared is equal to simply the sum of the two results. So vector a squared plus vector b squared minus 2 times the dot products plus vector a squared plus vector b squared plus 2 times the dot products. And these 2 times dot products both cancel. We're left with 2 of each, so that's going to be 2 times the magnitude of a squared plus 2 times the magnitude of vector b squared, and that's as required. That's what we were asked to prove. So I think this proof really hinges on knowing these two results. And as I mentioned, just in case you aren't familiar, what I'll do is I might just now take a bit of time to prove these because they are very handy. I've seen them come up in quite a few questions. So I might just turn over to do this, and I might just draw a fresh triangle to refer to in this proof. So let's just I might use similar notations. So we'll go we'll call this triangle OAB. We'll call OA vector A. We'll call OB vector B. And we'll call this angle in between those two vectors theta. And hopefully from what we just did, you can see quite quickly that vector AB is vector B minus vector A, because the way you can get there is you go from A to O, O to B. Going A to O is the negative of this vector, and then adding vector B. So what we can do to prove the first result is to use the cosine rule. And according to that rule, the magnitude of AB, of that side, squared, would be equal to the magnitude of OA squared plus the magnitude of OB squared minus 2 times OA times OB times the cos of the angle between those two sides. So that's the cosine rule. Now what we can do is just insert our vector notation. So AB squared is the vector b minus vector a, so the magnitude of b minus a squared is equal to the magnitude of a squared plus the magnitude of b squared minus 2 times the magnitude of a times the magnitude of b times cos theta. And that we can write as the magnitude of a squared plus the magnitude of b squared minus 2 times the dot product, since we have a result that hopefully you do learn. It's kind of one of the first things we learn with vectors, that the dot product of two vectors is you take their magnitudes and you multiply them, and then you multiply it by the cosine of the angle between them. So that's this bit here. So I've just then replaced this result in, and that's what gets us to this that we've relied on. So b minus a vectors squared is a vector squared plus b vector squared minus 2 times the dot product. So that's for b minus a. Now in terms of the other result, which is a vector plus b vector, I might just draw a different colour, because what we want to do is we want to go a vector, and then instead of taking the difference, we want to add on b vector. So if I was to kind of shift this vector over, I'm going to draw it up to here. This vector from O up to this point, which I might just call point C, this vector is vector A plus vector B. These vectors are identical, they have the same direction and the same magnitude. So this vector here is vector A plus vector B. And what I might do is I might call this angle here maybe angle alpha. Now, hopefully you see this is a kind of essentially a parallelogram. But the total of the interior angles, first of all, we can say that the opposite angles will be equal. So that will be theta and this angle will be alpha. And what we can say is that they're all going to add up to 360. So theta plus alpha would be the full 360 degrees. So 2 theta plus 2 alpha would be 360. So theta plus alpha would be 180, since we can divide the two. So alpha is just 180 minus theta. So that'll come in handy, because now what we're going to do is apply the cosine rule now to this triangle so that we get the a plus b. So if I say the magnitude of OC squared, that's going to be the magnitude of OA squared plus the magnitude of AC squared minus 2 times the magnitude of OA times the magnitude of AC times the cosine of alpha, but alpha we've just shown is 180 minus theta. So now if we put our vector notation, we'll get the magnitude of vector A plus vector B squared equals the magnitude of vector A squared plus the magnitude of vector B squared minus 2 times the magnitude of vector A times the magnitude of vector B times, now cos 180 minus theta, we can simplify that. That will essentially just be negative cos theta. And the way I get there is I use the rule cos A minus B is equal to cos A cos B plus sine A sine B. So therefore cos 180 minus theta would be cos 180 cos theta plus sine 180 sine theta. And that, if I just go to my calculator, the cosine of 180 is -1, so this would become negative cos theta. And the sine of 180 is just 0, so this would disappear. So that's how you can get the result that the cos 180 minus theta, we can just insert negative cos theta. So then we can write that as magnitude of A squared plus magnitude of B squared. These two negatives become a plus 2 magnitude of A, magnitude of B cos theta. And just like we did before, we can insert our dot product result. So plus 2 times the dot product of the two vectors. And that is the result that I've used for our A plus B squared. So those proofs, hopefully, they're fairly straightforward. They're just applying the cosine rule. You just need to kind of, for each one, think about two separate triangles and you know, apply a bit of trigonometry. But I think once you've proved it once, I think it is worth committing them to memory, because they're the kind of results that can come in handy for proofs like this. I think without these results, this proof would be quite difficult. You'd probably end up actually inadvertently probably proving these results anyway, just doing it the long way. So yeah, hopefully that's made sense. I think part A, fairly straightforward application of vector theory. And part B, I think tricky if you're not familiar with these results. So hopefully you found all that helpful and it's been useful for you. And tick boom.